Hello everyone, good day. So last meeting we had the proof by contradiction. Now, so we're done with the direct proof and the indirect proofs. So now let's go into proof by induction. Later, I think we need to distinguish when are we going to make use of the direct proof, the indirect proof, or the proof by induction. But that will be decided by us later after we go with all these topics that we had. So to start with the proof by induction, so allow me to give its description. So proof by mathematical induction is a method used to prove propositions of the form for all n, then p of n, where the domain of the universal set is the set of positive integers. Consider the following steps in proving by mathematical induction. The first step is to verify whether the p of 1 is true, meaning we can get an equal value of both sides for it to be equal. And then the second is, for the hypothesis of the induction, we try to assume that p of k is true, and then we prove that p of k plus 1 is true. Like we let our n be equal to k, we assume that it's true, and then we add 1 to the n that we have, no, and then let's try to check whether it's true, and then we conclude. Okay, let's have an example. So I had placed here in our screen the steps so that we can follow later. Allow me to have my pointer. Okay, so let's try to prove this example. Okay, prove that 1 plus 2 plus 3 plus the ellipses dot 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 plus n is equal to n times n plus 1 divided by 2. Okay, this one. Let's try to have this one. So this is our p of n, no? So let's try to prove this one. So step 1, verification. If n equals to 1, then we have 1 is equal to 1 times 1 plus 1 over 2. Asa man ito nakuha? Kana siya si n. Kani din siya kana siya this one. So is that equal? So you have 1 times 2 over 2. So 1 equals 1. So step 1 done. Okay, for the step 2, what we will do is that the hypothesis of the induction. Okay, let's have the hypothesis. So the first is assume that pk is true. So what is our pk? Assume that our pk 1 plus 2 plus 3 plus dot 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 plus k is equal to k times k plus 1 over 2 is true. Then prove that one plus 2 plus 3 plus dot 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 plus k plus k plus 1, the added one, is equal to k plus 1 times k plus 1 plus 1 over 2 is also true for n is equal to k plus 1. Here, I forgot, for n is equal to k. So let's try this one. Let's have our proof here. Okay, let's continue. So we assume that 1 plus 2 plus 3 plus dot 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 plus k is equal to k times k plus 1 over 2 is true for n equal to k. Then we prove that 1 plus 2 plus 3 plus dot 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 plus k plus 1 is equal to k plus 1 times k plus 1 plus 1 over 2 is also true. We can simplify this. This can become k plus 1 times k plus 2 over 2. Okay, so we need to get this one from this. So the first that we need to do is that write our assumption that 1 plus 2 plus 3 plus dot 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 plus k is equal to k times k plus 1 over 2. Now, let's substitute, let's add, no? I mean add k plus 1. What will happen? You will have 1 plus 2 plus 3 plus dot 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 plus k plus 1 is equal to k times k plus 1 over 2 plus k plus 1. So what we did was we just added k plus 1 and k plus 1 from our original equation. Okay, next, simplify. So if we will be simplifying this side, what will happen? We know that we have 1 plus 2 plus 3 plus dot 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 plus k plus 1 is this one. It is just equal to k plus 1 times k plus 2 over 2, right? Where did we get this? From our given. So we need to prove that this one is just equal with this one. So let's simplify this. K times k, that's k squared, plus 1 times k, that's k, over 2 plus k plus 1. So again, to simplify that, we can just have k squared plus k, and then we multiply 2 here as well as here. So you have 2k plus 2 over 2. So you will be having k squared plus 3k plus 2 over 2, which is just equal to, if you factor out this one, this will become k plus 1, k plus 2 over 2, which is equal with this. So since we got an equal left and right hand side, therefore we are able to prove that our n is equal to k plus 1 is also true. So for the step 3, where should I put it here? Step 3, conclusion. We can just say that since the statement from step 1 and step 2 are true, then P of n is true. Or our P of n is 1 plus 2 plus 3 plus dot 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 plus n is just equal to n times n plus 1 over 2. Okay, so this is our step 3. Okay. So I hope I was able to present it clearly. No? Okay, how about another example? So let's have example number 2. So we have here 1 plus 4 plus 9 plus 16 plus 25 plus the ellipsis plus n squared is equal to n times n plus 1 times 2n plus 1 divided by 6 for all values of n greater than or equal to 1. So we proved this by induction. So step 1, this is the verification part. So if n is equal to 1, then we can have 1 squared. Is it equal to 1 times 1 plus 1 times 2 times 1 plus 1 over 6? Are they equal? So 1 is equal to, I think this is 6, right? For 6. So 1 is equal to 1. So it's true. So we're done with the step 1. For the second step, we assume that 1 plus 4 plus 9 plus 16 plus 25 plus dot 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 plus k squared. So the n will become k is equal to k times k plus 1 times 2k plus 1 over 6 is true. So we assume that this is true. We will prove that if we add 1, 4 n equal to k. Prove that 1 plus 4 plus 9 plus 16 plus 25 plus dot 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 plus you have k squared there, so you can just add plus k plus 1 squared, no? Kaya siya. It's just equal to screen. Okay. Prove that 1 plus 4 plus 9 plus 16 plus 25 plus dot 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 plus, since this is k, prove that the k plus 1, so the k plus 1 squared is equal to k plus 1. So nanay plus 1 si k, kani k plus 1 plus 1, and then 2, so k plus 1 plus 1 over 6 is also true for n equal to k plus 1. You can simplify this one as k plus 1 times k plus 2, and then 2k plus, I think this is 3, because times 2 then plus 1 over 6. So we need to get this one. No? This will be our end of the proof for it to be equal. So I think we can make use of this vacant side here. So as a continuation, I think we can make use of that. Okay, so let's start our proof. So you have the assumption 1 plus 4 plus 9 plus 16 plus 25 plus dot 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 plus k squared. So we add k plus 1 squared from that, no? Okay, I'll just not complicate things first. Okay, so let's start. So let's start with our assumption. So our assumption is that 1 plus 4 plus 9 plus 16 plus 25 plus dot 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 plus k squared is equal to k times k plus 1 and then 2k plus 1 over 6 is true. So what we will do now is we need to arrive at this one, the k plus 1 squared. So I think we just have to add, no? K plus 1. 1 plus 4 plus 9 plus 16 plus 25 plus dot 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 plus k squared. So we add one term. The next term from k squared will be k plus 1 squared. So this is the next term, right? So we add k plus 1 squared. Same will happen in the opposite side. So you have k plus 1, 2k plus 1 over 6 plus our added term k plus 1 squared. Okay, so let's simplify that. If you have 1 plus 4 plus 9 plus 16 plus 25 plus dot 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 plus, since you can just have plus k plus 1 squared, because this will be the last term already. So if you will simplify this on the right side, you will have palabas natin si k plus 1 because they are the same. So go out k plus 1 and what's left inside will be k times 2k plus 1 over 6 plus k plus 1. Yan. This is k plus 1. Okay. Before we simplify this, we have a value of this one. Look at this one. This is the value. So the value for this one is k plus 1 times k plus 2, then 2k plus 3 over 6. That should be equal here to get the second as true. So we need to make this one similar with this for them to be true. So you can just have k plus 1. But if you simplify the inside, you will have, we can simplify it already. So 2k squared plus k, you can multiply 6 there. So that will become 6k plus 6 over 6. If you multiply everything, you can have k plus 1, and then everything can be over 6, right? And then you have this as 2k squared plus 7k plus 6, but you can factor it out as 2k plus 3 and then k plus 2. And if you look at this, they are the same. So I think we have proven that it's still true when k from k to k plus 1. So the step 3, so this is correct. For step 3, our conclusion, therefore, since step 1 and 2 are satisfied, the P of n is true. Or 1 plus 4 plus 9 plus 16 plus 25 plus dot 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 plus n squared is just equal to n times n plus 1, then 2n plus 1 for 6 is also true. I mean, is true. I think we're done with the proof for the second example. Now let's have another example. Example number 3. The example number 3 will be different in such a manner that it's more on divisibility. Like this is our problem. N cubed minus n is divisible by 3 for all the values of n greater than or equal to 1. Okay, prove this one, that this proposition is true by mathematical induction. Proof by induction. So let's have the step 1. We need to show that this is true when n is equal to 1. If n is equal to 1, then 1 cubed minus 1 is equal to 0. And 0 is divisible by 3. So this is true. Step 2. Assume that k cubed minus k is true for n equal k, then prove that k plus 1 cube minus k plus 1 is also true for n equals to k plus 1. So we need to show that. When I say is true, meaning it's divisible by 3. So we assume that k cubed minus 3 is divisible by 3. Then prove that k plus 1 quantity cube minus k plus 1 is also true, meaning divisible by 3. Okay, so let's show that one. So I think we cannot start with k minus 3. We are just given that it's divisible by 3. So we just make use of the second one, the k plus 1. So we know that k plus 1 cube minus k plus 1 need to be shown to be divisible by 3. But we can do that by making use of the assumption. We need to get this one, k3 minus k, because we are sure that it's divisible by 3. So we need to get a portion of this one as k minus k cube minus k to make it divisible. So I think we just have to show that if we factor out this one, we can get k cube minus 3. So with that, we just have to simplify. So k cube plus 1 is just k cube, no? Plus, I think it's 3k squared. And then plus 3k plus 1. How did we get this? We just multiply k plus 1 times k plus 1 times k plus 1. And then if you multiply this and then the answer to that, then you can get this. And then minus k minus 1, because that's negative here. So you can just give all the negatives. So if you simplify that, that will become, take note that you can have k cube and negative k, which is same here. So we can just factor it out. K cube minus k. And then plus what's remaining, we have 3k squared plus 3k, because I think this can be cancelled. But you can also simplify that, plus you can get out of the 3 and you have k squared plus k. We are sure that k cubed plus 3 is divisible by 3 by our assumption. And we are sure that this is also divisible by 3, correct? Because you can take note here. So you can just say that since k cubed minus k plus 3 times k squared plus k is divisible by 3, then n equal to k plus 1 is true. And then we're done with step 2. And then step 3, okay, since step 1 and 2 are satisfied, then P of n is true, or n cubed minus n is divisible by 3. Okay, we can just end with that, and then that's all. Okay, so I hope you learned something from our lesson today, and let's see each other next meeting.